Hello again. Thank you for joining us. This is Space Nuts, the podcast about astronomy and space science. My name is Andrew Dunkley, your host. It's good to have your company. Coming up on today's edition, we've got quite a few things to talk about. The ups and downs, or certainly not ups, of the Boeing Starliner. We'll have a quick chat about that. Lighting up the moon with reflectors is on the agenda, and using satellites to predict crop yields. Yes, they look down from space and go, oh, that looks crop. And we're going to look at a special anniversary with Professor Fred Watson, all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And here he is, the man of the millisecond, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. That was a pretty crappy introduction you did there, I have to say. But,
yes, I have to agree with you. Most of my introductions are. How you been? All well?
Yeah, well, thank you. All good. Still, it's going
good.
strong. Still astronomer at larging.
Yes.
For now.
Fair enough.
Yeah.
All right. Let's get started. I want to talk about the Boeing Starliner because I've been reading stories about it for the last week or so. They were so ramped up after years of delays. We were finally going to get it off the ground, and it slipped on a banana. I don't know what happened, but it looks like another delay.
It was, yes. So the crew of two. This was going to be the first crewed mission of the Starliner, and it was going to wind up at the International Space Station and probably come back from there as well. And the launch was set for Friday, our time. I think I'm right in saying that. I can't remember. I get so many.
I'll take your word for it.
Launch dates in my mind. These days you can look forward to a launch pretty well every day. Anyway, it was recently, maybe it wasn't Friday, I think that might have been Chang'e 6 that launched on Friday, which was also successful. The Starliner, however, I think they got to within 2 hours of liftoff, might be exaggerating there, and there was a sort of vibrating valve, I think, on the rocket itself rather than the Starliner, which caused the launch not just to be paused, but to be scrubbed. That was the official term scrubbed.
Ooh.
And in fact, you can find online, you can find the dialogue between mission control and the two astronauts in the capsule where they...
I've actually got it. Houston, beep, 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 thing.
Something like that.
I think that's how it went.
I mean, Houston, or its equivalent in 21st century speak, said, we're scrubbing the launch. And you could tell, it was Roger.
Yeah.
It wasn't Roger, it was Roger.
Roger wasn't happy.
I think the latest, I think they'd be happy to scrub anything that was imparting a risk to the launch. So I think you'd be happy with that. But yes, the disappointment when you're basically keyed up because, within a matter of hours, if not less, you're going to be docking at the International Space Station. Last I heard was that it scrubbed for at least 10 days. And in fact, I've just saw some photos this morning of the assembly, basically the rocket booster with the Starliner on top, being moved back to the kind of servicing bay that they've got there. Something a bit like that, vehicle assembly building that there is at Pad 39A. Anyway, so it's scrubbed for a while. So hopefully we will catch up with better news soon. It was pretty exciting. It will be, Boeing's first crewed mission to space.
Yes. Well, I'm sure it will happen, but as we've said many times in the past, safety first. So
Absolutely.
They're just being ultra careful, and who can blame them for that? All right, let's move on to the moon and back. This is a really interesting story because we're looking. There's so much interest in the moon. We've got a lot of missions either there or on their way there in the not too distant future. Human missions coming up soon. I know China's looking at putting a base there, whether it's on the surface or in orbit, a research base of some kind, and it's just going to get bigger and bigger. And the moon's got a lot of attention because, well, it's got resources there that people want. But when you get there and set up bases and have people there long term, there are challenges, and one of those is light. That's a problem.
It is. And yes, you're absolutely right. The South Pole in particular, which is a very heavily cratered region of the moon's surface, is attracting international attention because we have evidence from a number of spacecraft, actually, notably an Indian one, Chandrayaan, I think it was called, which the evidence supports the notion that there is water ice on the floor of these craters. Because being at the South Pole of the moon, the craters themselves never see the sun overhead or anything like overhead. It's always at an angle low down in the sky, and in most cases so low that it never rises above the walls of these craters. And so, the craters. And so the floor of the crater is basically, yes, it's got ice on it, which may have been there for millions, perhaps billions of years. But that ice is basically unobtainable because there's no sunlight, so you can't melt it, nor can you use electrical power to decompose it into hydrogen and oxygen, which is what everybody's keen on doing. It gives you a free supply of oxygen to breathe and hydrogen plus oxygen to make rocket fuel. So that's why there's so much interest in the ice in these craters as a potential resource for future exploration of not just the moon, but the solar system generally. So there's the problem. Solar power especially is a problem because these never see the sun. And that sort of thinking has led a group of scientists, some at Texas A&M University, some at NASA Langley Research Center, to think about how you deal with this. And they have basically done the obvious. They've said, well, why can't we reflect the light of the sun down into the crater? So you focus it onto the solar panels, and you've got a mirror near the rim of the crater. So that's the plan. The research, which is still apparently in quite an early stage, what they've done though is to use fairly sophisticated modeling systems, computer models, to show what will be the best kind of surface and the best sorts of materials as well to use. And it's no surprise that a parabolic shape comes out as being the optimal. That's because a paraboloid focuses light. That's what many telescope mirrors are made of, a paraboidal mirror that focuses the starlight onto it to make an image, which you then magnify with an eyepiece. So what you do with your mirror is steer it so it's always basically pointing at the sun in such a way that it reflects the light down to your solar panels, and have it on a mounting that will track the sun as it goes around the sky. Now, the other thing that I think is new about this is, two things here. One of the problems is you want to make your mirror as big as possible in order to collect as much sunlight as possible. But reflectors are not very easy to fold up into the cargo bay of a spacecraft, or at least its cargo pod in the nose of the spacecraft. And so you need something that will fold up. Now, we've encountered this problem before, Andrew, in a well-known thing called the James Webb Telescope, which was indeed folded up because it was made of 18 hexagonal segments that could be folded away. What they're thinking of for this, though, because the optical surfacing requirements are nowhere near as stringent, what they're thinking about is using new materials, and in particular, something which is called a self-morphing material, which has actually been developed at Texas A&M. So what you do is you have what they call shape memory materials, and change the shape in response to changes in temperature. And you'd certainly get a change in temperature when you go to the south pole of the moon, because the temperature when the sun's not there drops to about minus 150. When the sun's there, it's quite high. It's about plus 150. And so I think there's a bit of give and take in those levels, but it's that sort of order. So shape morphing materials that will kind of basically pop into the right shape when the sun gets on them are a nice idea. And maybe this is a way to the future for the south pole of the moon.
Maybe. Are you ready for this one?
Give it to me.
On reflection, that's a good idea.
You should be on the radio.
Oh, God. No, thanks. How much light are we talking about generating here?
A mirror's worth, I guess. There is a comparison, Andrew, and I've forgotten the name of the place, but there is a valley in Norway, southern Norway. It's not that far from Oslo. It's a valley that there's a town in the bottom of the valley that doesn't see the sun for, I don't know, a couple of months around the winter solstice, which of course means kind of November, December, January, that sort of time. And so they have a mirror on a hilltop that does see the sun and basically beams a pool of light. I think it's a flat mirror rather than a parabolic one. Beams a pool of light down into the town square so that people can, people who suffer from SADS, what's that, seasonal something disorder?
Winter blues.
Yeah, winter blues, which is pretty serious in those Scandinavian countries. So people can get a taste of sunlight without having to get on a jet to go to Mallorca or somewhere like that. The other thing that comes to mind with this is, and this is a bit off the track, but you've got to watch out for those focusing mirrors because there's a story, it's probably 3-4 years ago now, a new building in London, which had a glass surface as a skyscraper, glass surface that was slightly curved. And it was basically melting cars. Yeah, it was melting the insides of people's cars. Come back to their car and all the plastics melted onto the floor of the car.
Wow.
This building's focused the sunlight onto it. So that's not what
the other problem I heard with buildings like that is it causes bird problems. They don't realise it's actually a solid object because they can see a direct reflection of what's around and behind them. So they go boom, straight into it. Thousands of birds get killed every year from these situations.
Yes, that's right. That's unlikely to be an issue for the lunar astronauts.
On the moon?
Yes, but certainly it's on the Earth.
Yeah. You mentioned how cold it gets down in those craters on the moon. I stand to be corrected, but I do believe that at the bottom of some of those craters, it's the coldest place in the solar system, as far as I'm aware.
Yes, it's going to be. You're right that there are record breakers for the coldest place in the solar system, and I think I've read the same thing as you have. That the bottom of those craters, because they never see the sun, and thermal temperature losses, the thermal radiation that you get from those into the blackness of space probably do make them very cold indeed.
Yeah, I mean, I could be wrong about that. And there are so many very cold places in the solar system. So,
I think actually,
down the bottom.
Sorry, go ahead.
Go on.
I was going to say.
No,
We've got the delay problem here, Andrew. Both trying to talk over one another. I'm going to just continue. I think the coldest place in the solar system is in a laboratory somewhere in the United States where they've artificially created temperatures just a few, micro degrees above absolute zero. So, in fact, I think I've read that
either that or it's their management style.
Could be that too. Yeah.
All right. Lighting up the moon, a very interesting concept and one that will probably come to fruition We'll shed more light on that down the track. And you can find out more about it at phys.org. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, we mentioned an anniversary at the head of the program, 10 years of HIPPI.
Yeah, it isn't, it's for a start, it's such a brilliant acronym. But you're absolutely right. HIPPI has been going for 10 years. HIPPI is spelt not H-I-P-P-Y, but H-I-P-P-I. And it's an acronym for the High Precision Polarimetric Instrument. So HIP, High Precision PI, Polarimetric Instrument. That acronym's actually been very useful in the last day or so because people are wishing it a hippie birthday because it's 10 years old. So hippie birthday.
Well, I'll tell you my reaction. I've got the shakes.
Oh,
yes.
Think about
that one.
Yeah, hippie shake.
For goodness sake.
That's right.
Some people will get that.
Yeah, they will. Two of them. I got it. So the other one's out there somewhere. It's, well, to tell the story, what was celebrated yesterday, and just for reference, yesterday, our time was the 8th of May, 2024. On the 8th of May, 2014, HIPPI was first used on the Anglo-Australian telescope. I was at that time the astronomer in charge of the Anglo-Australian telescope, so I remember it all pretty well. But what I didn't realize at that time was just how powerful an instrument this was and what an illustrious life it was going to have down the track, as it has done for 10 years. So that machine has been evolved. It's now, HIPPI 2, which is the, it's the improved version. It's been used on the Anglo-Australian telescope. It's been used on the Gemini North telescope at Mauna Kea. So one of the biggest telescopes in the world, the 8.2 meter telescope, and a number of other telescopes as well, both in America and in Australia. So it's got a fabulous track record. It's brainchild, I guess. It's father figure, if I can put it that way. It was a colleague and friend of mine by the name of Jeremy Bailey. When he sent out a lovely notice yesterday advertising HIPPI's 10th birthday, and it's not online, it's just something that we know between astronomers, he basically included a list of all the publications that HIPPI has resulted in, which have come from 8,418 individual polarization measurements. That's pretty impressive.
What does it do?
What does it do?
It just sits in a corner and goes, "Hey, man, this is so cool."
Yeah, I think it'd be quite good if it did that. Sorry, you've put my train of thought in an entirely different direction there.
Yes, you're now reflecting on your youth.
Well, I'm actually reflecting on two people who and I won't say where they were or how we met them, but two people that we basically named Cheech and Chong, because that's what they were.
Yes, that's right. Yeah.
So
I
anyway,
remember.
The clue is in the acronym, High Precision Polarimetry Instrument. And polarimetry is about measuring polarized light. You can do it in radio waves as well, but that's with radio telescopes. This is an optical polarimetry instrument. And I'm sure Jeremy would cringe if he heard me saying this. Jeremy Bailey, the father figure, along with many of his colleagues at the University of New South Wales, I should mention that. That's where it was developed, here in Sydney. I'm sure they'd cringe at this analog. But yes, polarizing sunglasses. We're all familiar with polarizing sunglasses. And what they do, they take out the glare from a reflective surface. And that's because if light falls on a reflective surface, it becomes polarized. And what that means is that the vibrations of here we go.
These are my golf glasses.
Mr. Polarizing.
They're super polarized.
Fabulous.
Yeah.
That's good. Now,
Yeah,
for those
they
of
are.
you listening to this who can't see, Andrew looks extremely glamorous with a pair of polarizing sunglasses on.
God, I'll
In fact,
take my real glasses off.
I wish you'd keep them on all the time because,
Oh, wow.
yeah, it all fits with the hippie image, I have to say.
I'm cool.
Yeah, but if you now, if you kind of lift those off your head, Andrew, keep looking through them.
Yeah.
Pull them forward so that you can turn them round through a right angle. If you see what I mean, pull them forward and then twist them. No, not that way. The other axis. Yeah, that's
Like
all right.
that.
That's it. So when you look through one of those now, you're actually doing the opposite in terms of polarized light to what you do
Yep.
the other way. And you'll see light that's scattered off a reflective surface. And if you then turn them back to the way they normally should be, that'll disappear.
Oh, yeah.
There you
That's
go.
amazing. I've
Yeah.
never noticed that before.
So
But then again, I never wear them sideways. So.
No, you don't. Yeah, that's true. You don't wear them sideways. You look ridiculous if you did. Anyway, so what's happening there is that it's the way light waves vibrate. The vibration, the electromagnetic vibration of a propagating light wave is in kind of in all directions. But to put the polarizing sunglasses on, what you do is you just basically stream out most of those directions so that you've got these waves which are effectively representing a flat surface. I'm not really explaining it very well, but you're confining the vibrations into one plane, if I can put it that way. And that's what a polarizing sunglass does. Now, Hippi does that too, but in a much, much more sophisticated way. And whereas if you used your polarizing sunglasses to measure how much polarization there was in a beam of light, you might get it to 1 part in 10, something like that, an accuracy of that kind. Hippi can do that with an accuracy of 1 or 2 parts per million. And so it is incredibly high precision, hence the name, Hippi, High Precision Polarimetric Instrument. So it's got this unique ability, and it hasn't been surpassed by anything else in the world, to make these really superbly accurate measurements, all in a box about the size of a loaf of bread, which means not only was it very cheap to make, it's also one of the smallest frontline instruments in the world. In fact, Jeremy and his colleagues sent around a lovely photograph showing Hippi on the back end of the Gemini North telescope in Hawaii. The caption is "a very small instrument on a very large telescope." And Hippi weighs 15 kilograms, but in order to mount it on the back of the telescope, they've got to add 2 tons of counterweight, so it doesn't just spoil the balance of the telescope, because most astronomical instruments weigh several tons. So what's it done? Polarization is really useful for tracking magnetic fields in distant star systems, distant galaxies, because what happens is that magnetic fields tend to align the particles in clouds of dust. And we call it dust, but to anybody else, it's smoke in space. And those clouds of dust actually are essentially magnetic. They will align along the field lines of a magnetic field. And the dust also polarizes the light that passes through them. And so what you've got is an instrument that can measure very accurately the magnetism at very great distances. Galaxies at the other side of the universe can have their magnetic fields measured, not because you've got a bar magnet to hold up or anything, but because you've got a polarimeter. And so that's the kind of science that it does. But it can also, and I love this, Jeremy once told me this and I've been blown away by it ever since. You know that you probably don't know, but again, you should check this with your polarizing sunglasses. If you're on the golf course with those sunglasses on, Andrew, and you have a shower of rain and you see a rainbow, check the rainbow out through your sunglasses and do that same trick of bending turning your sunglasses through 90 degrees. And you'll see that the light from the rainbow is very, very highly polarized. In fact, some polarizing angles, it disappears altogether. So rainbows are things that polarize light very efficiently. And Hippi is capable, because of this, of detecting rainbows in the atmospheres of exoplanets. Work that one out. You can find
that's
rainbows
amazing.
on other worlds in orbit around other stars. What a brilliant thing to look for. I don't know whether Jeremy's ever detected that. I think the last time I spoke to him, he hadn't. But it's certainly one of the possibilities for this kind of astronomy, that you might be able to detect rainbows on other worlds. What a wonderful idea.
Incredible. Yeah, what a great instrument. Happy birthday to Hipie, as 10 years old. In fact, we'll go hippie, hippie, hooray.
Yes. I'm glad you said that, because
Yeah, I wish I hadn't.
No, I'm glad you did. There were several emails back to Jeremy yesterday that said exactly that. Hippie birthday.
Stealing my ideas.
Hippie, hippie, hooray. Yes, they are. They're stealing your arrays.
All right, to our final story today, Fred, and this one is the use of satellites to predict crop yields. Now, this sounds like, it doesn't sound beyond the realms of possibility. I'm sure 50 years ago they would have said, oh, hogwash, can't be done, never happen. But it is happening.
It is. It's basically a framework that has been put in place to essentially, and this is actually coming from the one of the press releases about this idea, and arises in Cornell University in the United States. The idea is to produce this framework, and by that I mean a kind of a system framework that would let you predict agricultural yields using minimal data. That's the trick here. You're using as little information as you can from a spacecraft to be able to predict the agricultural yield of what's on the ground. And the reason why that's important is that if you've got, if you're a farmer in Australia, you're a farmer in the United States, farmer in Europe, you would have resources that would let you do that on the ground. You'd be able to go and check your crops and say, well, this is going to be a bumper harvest, or this is going to be not a croppy harvest, if I can quote you from the beginning. It's going to be rubbish. But if you imagine yourself in a developing nation with yields that might be highly dependent on weather conditions and virtually no technology to be able to use to work out whether your crop's going to fail or not, that is the whole idea of that. And so the basic premise of this whole work is that from space you can measure essentially the color of the crop, and by that I mean not just whether it's green or yellow, but the subtleties of its spectrum. So you can look at the spectrum of a paddock or a field of crops from space and analyze the colors in it. And what you can look for is something called chlorophyll fluorescence. Now, we're all kind of familiar with chlorophyll. It's what gives like grass and trees their green color. And basically, it's the photosynthesis mechanism in crops. It's what actually allows light to turn the chemicals in those crops into useful things that nourish it and also provide oxygen. So chlorophyll fluorescence means that if the sun is shining on it, then you get chlorophyll fluorescence being formed, and then it's a reddish color that's emitted by photosynthetic tissues, and you can measure that from space, and you can do it pretty accurately. So it means that you're not really getting an instant measurement of what the yield will be, but it does tell you about the health of that crop on the ground, how well it's doing, and what sort of yield you're likely to get at the end of the day. And so, yes, it's very much aimed at, first of all, as I said, developing nations, but also the fact that a lot of traditional cropping methods are starting to break down because of climate change. And so climate change, again, is very much an important part of this story.
Yes, one of the crops that's under major threat is coffee, because they need to grow coffee beans at high altitude, and it's getting too warm. So it's only a certain height they can go, and it could jeopardize future coffee crops. Satellite technology is synonymous with agriculture these days. And in my part of the world, where we have big, huge farms that grow wheat and canola and sorghum and you name it, the harvesters are actually satellite controlled. They're all geo-controlled from space. You can you sit in the cabin and watch movies while it just does it all by itself. It's quite incredible. It's all satellite controlled.
It is remarkable. And that comes from, it's probably now 6 years ago. I seem to remember this was part of the 2018 kind of kickoff when the Space Agency was formed. Geosciences Australia got grants to do exactly what you've said, to use satellites to control planters, harvesters, all the other agricultural machines. But it's more than just giving the driver a rest. It's about high precision farming, so that you can go within a millimetre of the edge of your paddock, where the ground falls away. You can get so close to that, you can have very, very high efficiency in the yields of the land. And that was what they were talking about at that time, how you can improve the yield by high precision farming.
I imagine it would also be they'd be able to calculate the best combination of manoeuvres to get the crop off with the lowest amount of fuel use, things like that. It's quite amazing. But crop. I can see this being an incredible tool going forward for farming. Being able to just take a peek at your crop and going, okay, I'm selling the farm, or I'm going to buy another one.
Yes, that's right. That's it.
Depending on yields. Yeah, fantastic. That story, if you're interested, is on seeddaily.com. I know we do have a lot of people in agricultural areas that do listen to us, so seeddaily.com is where you'll find that story. Fred, that brings us to the end. A reminder, if you'd like to visit our website, you can do that at spacenutspodcast.com or spacenuts.io. If you've been following us on YouTube, don't forget to subscribe below. And please leave reviews. Reviews are very handy to spread the word and get more people on board with Space Nuts. So, yes, please leave reviews on whatever platform you use. We'd really appreciate that. Fred, as always, it's been a great pleasure, and we will catch up with you again real soon. Probably could be minutes. You never know.
Well, it could be. That's a bit unlikely, but it could be.
All right. Thanks, Fred. We'll see you soon.
Sounds great. Thanks, Andrew.
Fred Watson, astronomer at large, part of the team here at Space Nuts, and Hugh in the studio, who's been watching all sorts of crop on his television lately, and I'm not really going to get into that too deeply. Scary stuff. And from me, Andrew Dunkley, thanks for your company. I will join you again, as will Fred, on the next episode of Space Nuts. See you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at bytes.com.
This has been another quality podcast production from bytes.com.